Hello, this is Paul from Tech. In this video, let's prove Theorem 4.6.4. Determine if a set of vectors is a basis. And usually, or by the definition of a basis, if we need to say a set of vectors is a basis, we need to look at two conditions. And the first one, the set as span the whole space. The second is S is linearly independent. However, this theorem gives us a special. Okay, so if we add one more extra condition, if the dimension of the vector is n and S has exactly n vectors, if in this special case, see, what do we need to say? If we need to prove S is a basis, we only need to look at half of the condition. Either S span V or S is linearly independent. Okay, this or is not an and. Let me give an example. Let me just show you example. See, let's say the dimension of V is 2, okay, as small as possible. If the dimension is 2, so I should give S, okay, it's only two vectors, like a V1 and V2. And now we can prove, okay, the theorem says we only need to say one condition holds, and then S is a basis. See, two results. The first, say the first S span, okay, V, or we say the span of S equals V, then S is a basis. And the second, if S is linearly independent, then S is also a basis. Okay, so these two is just the theorem. So now let's see why the first, the second is correct. The dimension is 2, and the S has two vectors. So we look at it first. If the span of S equals the whole space, S is basis. By the definition of basis, we only need to see this V1, V2 is linearly independent, right? So for the first, we only need to say we need to prove this. We need to prove okay. The span of S is V. We need to say S is linearly independent. Why? Two vector span S is linearly independent, so it's not difficult. So we can say we can prove by use the proof by contradiction. If S is not linearly independent, then it's linearly dependent. Okay, so we can see if S is linearly dependent, what does it mean? We need to find a contradiction. Linearly dependent. If S is linearly dependent, let's say the second vector V2 is a linear combination of V1. Okay, so then we have by the minus, okay, by the minus theorem, which is 4.6.3. What do we have? V1, V2, if V2 as a linear combination of the other vectors, so we can minus V2 from the set, and then we will have this the span of V1 should be the span of the original, which is V, right? So the span of V1 equals the span of V1, V2 equals V. Oh, these contradict, right? Why? Okay, so this is not correct. It's what? Contradict. By the previous theorem we have, which is theorem 4.6.2, B, the second part. Why? This theorem, the previous theorem says, okay, if V1, V2 is a basis of the space, and V1 is a set of vectors is less than the number of bases, then the span should be not equal to the whole space. Okay, but now you say the span equal to the whole space, that contradicts. If it's contradicted, it means what? Means S is not linearly dependent, therefore S is linearly independent. So we have a conclusion. S is linearly independent. Yeah. See, we get S is linearly independent. It's true. Now look at the second. The second case, if S is linearly independent, S is V1, V2. The dimension is 2. And then we need to prove S is a basis. By the definition, we only need to say S, the span of S equals V, right? Okay, so now that's the one we need to prove. The second, we only need to prove if S is linearly independent, then span of S is the whole space. Okay, so we look at it. The two vector is linearly independent. Why? The two vectors span the whole space V. What is V? V is the whole space. And the dimension is 2, right? Okay. The dimension is 2 means we should have 2 vectors in a basis. So now S we definitely has 2 bases, has 2 vectors. It's linear independent. And S need to be a basis, so we need to say the span equals V. What if the span is not V? Okay, we can just prove by contradiction again. If the span of S is not V, which means belongs or included in V, but it does not equal to each other, which means the S is smaller than the whole space. Okay, and what does this mean? This means we definitely can find then exists the third vector, right? Belongs to V, but this V3 does not belong to the span of S, which is V1 and V2, right? Because the span of S is smaller. What does this mean? Okay, this means that we find that a new vector is not in the span by the plus theorem we just have. So by plus theorem again is 4.6.3. Okay, what do we have? We will have this. We plus the new vector V3 into the original V1, V2. Should be linearly independent. V1, V2, and V3 is linearly independent. Because the original V1, V2 is linearly independent, and then V3 does not belong to the span. Okay, so we have this result. Is this good? Of course not. Okay, this contradict. Contradicted to what? Contradicted to the previous theorem, 4.6.2.8. What does that mean? That theorem says if we have the basis 2 vector, okay, we have 2 vector in the basis V1, V2, okay, whatever, okay, because the dimension is 2, so we should have 2 vectors in a basis. But now this set, okay, is what? This set has 3 vector, more vector than the vector in the basis. This should be linearly dependent. But now here is linearly independent. That's wrong, right? So this is impossible, okay? It's impossible means that the span should be equal to the whole space. Now we get a conclusion. That's the proof. Thank you.